All right. Today we are actually going to finish out chapter 20. So the test is next week. There's a week from today will be the review. A week from Thursday is the test itself. Today we are going to talk about the last section in chapter 20. And Thursday we're actually going to be in the lab. We'll talk more about that in a little bit. But that's basically the next 4 class periods. So today we have the last section in chapter 20. Thursday we'll be in the lab. Then we'll have the review period and the test. So, anyway, section 3 of chapter 20. It's called electrolysis. And electrolysis is really any time you use electricity to make a chemical reaction happen. There's a lot of different things that we can do with electrolysis. We've actually sort of touched on them a little bit already. If we have, if we just go back to this is the very first voltaic cell that we ever talked about. So if we have zinc with the zinc ions, and we had copper ions, and potassium chloride sulfate. Okay. If we connect these with a wire, we're going to get electrons moving from our zinc to our copper. Okay. But if instead of just connecting a wire here, if we put another power source, okay, so it's supposed to be a lightning bolt because they say that for power. Anyway, so if we put a power source and we hook it up correctly, well, electricity is just moving electrons. So if we are forcing these electrons to go this way, we can reverse the reaction. And instead of having zinc coming off because it's losing electrons, okay, we're going to have copper coming off as it loses electrons, and the zinc ions are going to come and stick on our zinc electrode right there. So we can reverse this reaction that originally was creating electricity, but now if we use more electricity than this can create, we can force it to go backwards. Well, that's the whole point of secondary batteries, rechargeable batteries. Every time you plug your phone in or plug in the computer to recharge the laptop battery, this is what's happening. You have an external power source that is driving the electrons the opposite direction of where they would normally flow in this redox reaction. And so what happens in a battery, we do this until we've used up all of what we can over here, and the battery is fully charged. And then we can remove the external power source, and when it's just normal, things are going to flow that direction again. And so in a battery, you flow and it moves and uses all that. And then it'll die and you can plug it back in. And it goes back and forth, back and forth. Okay. So recharging a battery is an electrolysis reaction. And that's just one example. In this section, we're going to talk about a number of different examples of electrolysis. And actually, electrolysis is what we're going to be doing on Thursday. So now, one very simple electrolysis reaction, and honestly one that you do at your house without any real trouble. So you get just a cup of water, and you need to add a little bit of electrolyte to allow the water to flow, or the electricity to flow, I should say. Salt goes well. So put a little bit of salt in the water. And then just take 2 wires from a battery, put them on either side of this cup of water. As the electricity flows, it actually will do this electrolysis, and what happens is we're separating the hydrogen and the oxygen in water. So as the electricity is flowing, you'll notice bubbles starting to form at each of these wires. On one side is going to be hydrogen bubbles, and on the other side it's going to be oxygen bubbles. Okay. That's pretty simple electrolysis. Like I said, use a battery, not a plug into the wall, because that's too much power and that's dangerous. But that is, if we need hydrogen for something, that's one way that we can get hydrogen, is simply the electrolysis of water. Water is pretty abundant. If you just need hydrogen, it doesn't have to be drinkable water. And so, yeah, we can do that. There's another example that it gives. In this case, we are, instead of water, we are going to be doing sodium chloride, salt. Okay. Now, in order to do electrolysis for salt, it has to be in a liquid form. It does, so sodium chloride will melt if you get it hot enough. If I remember correctly, it's up around 800 degrees Celsius where salt will liquefy, it will melt. So you have to heat it up and then start running the electricity through it. So what's the point of doing this electrolysis on sodium chloride? Well, sodium by itself, very reactive. Okay? We don't find sodium in nature just by itself in its pure metal form because it reacts. Same thing with chlorine gas. We don't really find big deposits of chlorine gas. It's very reactive, and it's going to form compounds instead of just sit there waiting to be mined. Now, when we very first talked about ionic compounds, we said, okay, we've got sodium here with its 1 valence electron, and chlorine, okay, we'll swap one of them for now. In a balanced reaction, we have 2 of these reacting with 1 chlorine molecule, but anyway, so it's going to have 7 valence electrons. And when we bring them together, because sodium can lose this to get to a full valence shell, Chlorine can gain one to get to a full valence shell. So now, both of these have a full valence shell, and that's what we're talking about. But if we look at it closer, well, what's happening? An electron is moving from one atom to another. That's redox. Okay. So that's a redox reaction. So in electrolysis, well, we're using electricity to force a reaction to happen that wouldn't normally. And just like in a battery, how we're forcing it backwards, that's what we're doing here. Okay. When we have molten sodium chloride and we do the electrolysis, we can get sodium metal and chlorine gas. That is a great source for these two elements that otherwise we don't find by themselves in nature. We have to purify them. We do, however, find a whole bunch of salt. Salt is plentiful and very inexpensive. If you ever have to go to the store to buy salt, it's dirt cheap because there's so much of it. And so, in order to get these compounds, this isn't the only way, but this is one way that we can do it. We harvest salt, heat it up, melt it, run the charge through it, and we can extract these elements. So, we use these different elements in several applications. The chlorine, we can use it as a disinfectant, like we would treat water with chlorine and that kills off things in it. A lot of cleaning products have chlorine. A lot of swimming pools use chlorine, stuff like that. Sodium, you can actually use sodium in nuclear reactors, which is it's a coolant rather than fuel, but we can put it in something called a sodium vapor lamp. So these are bright lights. So there's other uses. Anyway, this is one way that we can get them because they aren't found in nature like that. Now, the next example that the book gives is actually very, very similar because we're going to be using sodium chloride again. But instead of pure sodium chloride that we heat up to melt it, we're going to be doing the electrolysis of what's called brine. And brine is basically just salt water. Okay. So what we do, and there is, this whole setup has a picture on page 730. We have brine that's coming into a system. Okay. And this system is in two different compartments. And on one side, the brine is coming in, and that's where we have the anode, positive side. This is where chloride ions, because remember, when we dissolve it, we're going to have a bunch of these ions dissolved in the water. Okay. So we've got the chloride ions. It has the extra electron. Okay. That's why it's going to react at the anode, where we have oxidation. It's going to lose that extra electron, and we're going to get chlorine gas. Okay. Separating these two chambers that we talked about, there is a special, basically, barrier that will allow ions to pass over, but not the big molecules of water. So these sodium ions are able to pass onto the other side, where we have our cathode. At this point, the sodium is actually not going to be reduced. We're not going to get sodium metal out of this. The reason for that is that the hydrogen is more likely to be reduced than the sodium. Okay? It's easier to reduce the hydrogen in water than to reduce sodium ions. So that's what we get. We start to get this reduction of the hydrogen in the water. Now that, if we pull the hydrogen, one hydrogen out of water, we're left with OH minus. Well, these two can pair up to give us sodium hydroxide. So this process, the electrolysis of brine, it gives us 3 different products that are useful. We have chlorine gas, we have hydrogen gas, and we have sodium hydroxide. All through the electrolysis of salt water. Okay, now, like I said, you have to have the specialized equipment with the ion permeable membrane in order to get this to work the way it is. You also have to have the concentrations right. You can't just have salt water and throw some electrodes in there, because like we said, in that case, you're just going to get hydrogen and oxygen. So. Then book talks about aluminum. Now today, aluminum is everywhere. We have drinks in aluminum cans, food in aluminum. We use aluminum in structures, in airplanes, and things like that. We just sort of take for granted that aluminum is widely available. But that hasn't always been the case. Okay? It wasn't until the late 1800s that aluminum started to become more available. In fact, in the earlier 1800s, aluminum was more expensive than gold, mostly because it was really, really difficult to extract it. So there's a lot of aluminum out there that we can, dig up out of the ground. Problem is, it's not pure elemental aluminum. It's in these other compounds. Okay? One of the big compounds is bauxite, okay? Which is an aluminum oxide. And yes, we could purify bauxite into elemental aluminum, but it was a very labor-intensive process and had to be done in small batches. And so large quantities of aluminum you really couldn't find. And if you could, they were very, very expensive. So, we have, at the end of the 1800s, actually 2 different scientists that figure out a way to do electrolysis. They weren't working together, but right around the same time, they both figured it out. So they're both pretty much credited for this process. Anyway, it is a fairly energy-intensive process. Okay? Now, it absolutely did make it so that we could get more aluminum. And it drastically brought the price of aluminum down. But like I said, it's still a very high demand as far as electricity goes. It uses a whole lot of electricity. If you're going to be using this process to produce electricity or to produce aluminum, you've got to have a very cheap source of electricity. Earlier, and still to this day, just because, they haven't moved these places. A lot of times what you'll find is these aluminum refineries are very close to hydroelectric dams because, well, once you've built the dam, it's just the force of water that's generating the electricity. You don't have to buy fuels and things like that. And so it is, once you have the dam, it's a very cheap source of electricity because if you're going to be using a ton of electricity, you want it to be cheap. That is why a lot of aluminum recycling is encouraged because it uses a lot less energy to recycle aluminum than it does to purify it. Really, to recycle aluminum, all you have to do is melt it down. So, electrolysis, there are plenty of other ores that electrolysis can be used. We're not going to go through all of them, though. There is one other type of electrolysis that we want to talk about, though. And it's called electroplating. Now, electroplating is using electrolysis to coat a specific metal with a different metal. There can be a lot of reasons why we do this. But the two biggest ones, I would say, are appearance and protection. So obviously, when we talked about galvanization, we said, we've got this coat of zinc. And we can use electroplating in order to coat the iron with zinc. We can also coat iron with a number of different substances to protect it from rusting other than zinc. So on a car, sometimes you'll have like chrome plated pieces. That is electroplating. You take the cheaper iron and you coat it in, well, true chrome has several different chemicals that they coat it into using this electroplating idea. So what it actually is, well, it's just like what we were talking about with the reversing that voltaic cell, where you said we have these ions in solution that are going to be put onto the cathode. Now you can do this a couple different ways. You can just have the ions in a solution already, or what they have set up here in the book. If you have the metal that you want to coat, so what they're using is silver. So they've got a fork and they want to put silver all around it. Okay. So they're using their anode is just silver. Because at the anode, what happens is it loses the electrons and goes into solution. So if you just have a chunk of silver as your anode, because of the way that you've hooked up your power source, it's going to start drawing electrons from the anode, which is going to put those silver ions into solution, but the electrons are traveling towards the anode, or the cathode, I should say, traveling towards the cathode, and that is going to start pulling those ions out of solution. And so we can have basically this redox reaction with the same element. First, we have it coming off the anode, and then we have it coming onto the cathode. But electroplating is, fairly common. I think it's a great way to coat metals. A lot of times we'll use a cheaper metal and then coat it with a little bit nicer looking metal. For example, you have, if you want something to look like it is a gold coin, but you don't want to actually have to have a gold coin, take an iron, they typically call it a slug, an iron slug that looks like what you would want the gold coin to look like, and you just put a very thin layer of gold around it. It looks like a gold coin. Now, it doesn't have all the same properties of a gold coin. There were people who figured this out and tried to basically, cheat people, saying, look, I'm going to pay you this gold coin, when really it was just iron. And so if you ever see, like in a movie, somebody bites the coin, because gold is a very soft metal and you can leave a tooth mark in it. And so that is them making sure that it is an actual gold coin and not a gold-plated iron coin, which is not nearly as valuable. So, also, my ring, this is what's called white gold. So it has just traditional yellow gold underneath, but then it is electroplated with rhodium, which gives it that color. So, electroplating is a very widely used process and has a lot of very useful applications. So that's actually the end of this chapter. So we're going to talk about the lab. That's the word I was looking for. There is a quick homework assignment as well. I'll put that up here just before I forget. It's 55 through 63. Most of them are pretty short, simple questions. So anyway, like I said, we're going to be doing electrolysis. And I'll give you that. So honestly, it's pretty darn straightforward what we're going to be doing. Okay. Mostly what we're going to be doing is we have some different solutions that we're going to be using, and we are going to run some electricity through them. Now, we're going to be using this to do our reactions. You'll notice there are 3 different sections here. Okay. We have different reactions that we're going to do, and this allows us to, just do them all in one spot. So we're going to be using this, and now the instructions say that we're going to be using 9-volt batteries. Instead, we're going to be using our battery eliminator. Okay. This basically, it plugs in and it acts like a battery. So this little dial here goes to different voltages because this was designed for 9 volts. I'm going to keep it at 9 volts. Okay. It'll plug in. This is, out here, even though we plugged into the wall, because of the mechanism in here, these are very safe, right? When it's plugged in, you can actually grab them with your hands and it's not going to shock you. It's just like if you would take a battery and put your fingers on either side. So we're going to use this, and basically, like I said, what we're going to do, there's several different setups, okay? Like the first one, it says we've got our potassium iodide and phenolphthalein, and then we put our electrodes in, okay? And that's pretty much as complicated as it's going to get, and then we're going to make observations about what's happening. Now, our electrodes can be pencil lead. Okay. This is 0.9 millimeter pencil lead, so it's pretty thick as far as pencil lead goes. That being said, it still does break fairly easily, so try not to break it. But we are going to use these because, well, graphite conducts electricity. So we're going to take one of these out and carefully put it in like that, and it will conduct the electricity. And then we stick 2 of them. You want to keep them on opposite sides of the compartment, mostly because if the electrodes can touch, then instead of doing electrolysis, they're just going to pass the electrons through there. It's going to short circuit everything, and you won't get the reaction. So put them in there. Like it says, let it run for 1 to 2 minutes. Make your observations. Okay. Then we're going to pull them out, rinse them off a little bit. Okay. And then we've got a couple of other things that we're going to do. Okay. So add a couple drops of a starch solution. Okay. And record our observations. Then we're going to move on to a sodium chloride solution. Okay. Phenolphthaleins. We're going to do the same thing. Okay. We're going to put in our electrodes. We're going to record our observations in the table. Okay. The table is right here. Okay. And after that, we are going to do a copper bromide solution. Do the electrolysis and make our observations. Okay. The solutions, you don't want to have them go down the drain because there's possibility of some halogen solutions, which are not great. They have to be treated. So don't pour them down the drain. We have specific disposal that we'll go through. So that is going to be next class period. We'll do that. And then it probably will not take the entire class period. And so you'll have plenty of time to do the post-lab workup. Probably be able to, if not finish, get really close to finishing that. So at least that would be that's my guess. If it does take the whole period, then, whatever, it's not a problem. But anyway, so that is the reaction or the lab that we're going to do on Thursday. And then I will stop talking and you can get started on homework.